Yeah, we'll use this in all sorts of ways. And I swear to God, I'm going to get you, clean up these notes and get them to you soon. So, it'll take us a little while to really put this to use like we should, but I'm going to play around with this. At least I'll play around with stopping times a bit more. Okay, so remember my beloved Poisson inequality. I said we get conclusions without almost any assumptions at all in the process. I'm going to generalize this a little bit. I've got a function v, a function f, a function g, all non-negative, and I've got dv is less equal to minus f plus g. Yep. Oh, you were absent during all this exciting discussion. This poor person now has to see applications. So we actually developed some quantum theory while you were gone. Yeah. Okay. Oh no. So you were in for the zetas and so zetas is stopping time, and I won't review what that means. But the main thing. Oh, cool. All right. Okay. But anyway, you can think of if you don't know, you can just in your mind just think of the first return time to a set. So. So I defined stopping times. I'm changing my zeta to a tau because I've got a tau a there, and that's why I'm going to be using this. I said that it was took values in the integers. We're going to allow infinite integers as well. You know? So if this holds, then for any stopping time tau, the expectation of the sum. Oh, actually, I should write this out differently. Actually, well, forget it. Nah. Well, I'm so tempted to put more into this, but I won't. That is what I want. Yep. Okay, so there's a grand theorem. So So no assumptions at all, except for I've got a Markov chain. V, F, and G are equal to 0. They could even take on infinite values, you know. And you know, it doesn't even matter. Tau could be identically infinity. And it's, you know, it doesn't matter. You know, this is always true. So it's really powerful that you can have this very weak assumption and get something without any other assumptions at all for any Markov chain. So we call this the comparison theorem in our book. You know, a grand name for a very simple result. It just turns out to be kind of useful. So what do we do with this? So I said I was going to play around with martingales. There's a martingale hiding there. That's the point. So here's the game. So first of all, you recognize this, right? This looks familiar. You know, I had my Poisson inequality before. F was C. It was a cost function. G was a constant. We called it eta bar. All right. So that looks like tau times eta bar. You know, go back and look at your notes. And that's the sum from 0 to tau of the cost. The only difference is that now tau is random and G is not constant. So go back, because it's just a generalization of what we saw before. The most important generalization is that tau is random now. Okay? And what you need to do is to know that this is a something or other. It's a super martingale. So, you know, super meaning not super. It means it's unfortunately not a martingale. Super is a bad thing here. But so okay, so yeah, let's take f and g to be finite valued, so we don't have infinity minus infinity. Besides that, forget it. I mean, they're all finite valued. So this holds automatically under that condition. It's really the definitions, you know, because P defines the conditional expectation. If you look at m at time n plus 1, it's got this thing, which is in the future. And then here you end up summing from 0 to n. It's all in the present and past. Okay, so this randomness is known, so it comes out of the conditional expectation. You see, this is the discussion we had earlier. This is still a random variable. Yeah. Yeah.
I missed why you drew that arrow there.
Well, because I'm claiming this is equivalent to this being a super martingale. It's the same thing. It's just.
It's to reveal.
What?
So in a martingale case, it would be an equality.
Yeah, that's right. So the super corresponds to the inequality. Yeah.
And it's the other way.
It's a sub martingale. Yeah. That's right. And it comes from harmonic and superharmonic.
So like the super martingale, correct me if I'm wrong, will be the model that is in the casinos, right?
No. Oh yeah, in terms of your wealth disappearing. Yeah, that's right. Exactly. Except maybe some geometric sense. If you're stronger, you die.
Was it the Brownian thing?
What's that?
For the casino?
No, I mean, that's, well, the statement was correct, but you can strengthen it. I mean, you can, yeah.
I feel like the name should be flipped, though.
No, but it comes from harmonic and superharmonic. It comes from mathematics, from other disciplines. I know what you mean.
It seems like it's getting smaller.
Absolutely, but in terms of other definitions of mathematics, it's consistent. And so you go then plug this in. Now, oh, damn. Remember, this D is P minus I, so it's the same as writing that, right? And P is a conditional expectation. So exercise, PV, given Fn, I plug in Xn. We've done this before. Okay, so I'm not repeating this step because we've done it in the last couple of lectures. You know, we've said we've said that this PV defines exactly that conditional expectation. That this conditional expectation exactly PV, but evaluated at Xn. You know, and so this we said was less than or equal to V minus F plus G. V minus F plus G evaluated at Xn. All right, burn that into your brains. And you see that you lose the last term in this sum. Okay, so the minus F plus G cancels the plus F minus G for time t equals n. All right, and so then, you know, you can pick up encyclopedias on martingales and super martingales and pick out all sorts of cute results. You know, which we won't, but you could. You know, there's just huge results. There's people have devoted their lives to studying martingales. Okay, and so what starts out as some dumb little thing ends up bringing open a treasure chest of tools. Yeah.
It was so weird how that comes about.
Yeah, where did I used to know it? You know, martingales on a horse, something to keep their heads level. It's part of that, and. You know, it's yeah. God, I'll come back with it. I've forgotten. You know, but it comes from anyone knows anything about horses? A martingale is something that is used to level out a horse's head. Is what I recall. I'll come back with it. So okay. Anyway, so this is the trick to replacing the n with a tau. And unfortunately, I have to sort of just cheat and say, well, it's a fact that martingales have a nice property. So, you know, we know that so you can go through and you can iterate this. You know, you can take the expectation of both sides. Take the conditional expectation given Fn minus 1, and it'll go down. Take the conditional expectation given Fn minus 2, and go down. So you get that you can eventually get the expectation of Mn is less than or equal to expectation of M0. You also get the expectation of M of tau is less than or equal to the expectation M0, but not no. Only if you put conditions on everything. So that's if So unfortunately, there's a big caveat for the second one. We have to have an assumption on M that will never be satisfied. You know, I told you I'm not putting any conditions on tau. You know, tau could be infinite valued always, and this is still true. So how on earth could I use a result like that when I'm not putting any conditions on tau here? So think back about all these theorems from stochastic methods 1, all these results. You know, where you bound things and then you unbound them. So first you establish this result for tau's. This now holds. Let me just write it down first. Yeah.
I missed a little bit of the flow here. So
yeah.
Equality to inequality.
Well, I never had. This is a definition.
That's the definition. I see that. Okay.
Yeah. And then here I just said that. Go back to your notes. Saying PV is a conditional expectation. So that is precisely PV evaluated at xn. Okay. All right. And so I just plugged in that conditional expectation is less than that. See? These two guys, that guy's less than equal to that. Yeah. Okay.
Then what
yeah. And well, then things cancel out. I mean, remember, here's my definition of Mn. Okay. It's got a V of xn. Check. It's got a sum from 0 to n minus 1. There's an n there, but it gets canceled by the last term gets canceled off. So it does become a sum from 0 to n minus 1 in this line. This whole thing, I just didn't want to write down this again.
Okay, thanks.
Yeah, okay? All right. So can you see that this is exactly that, all right? Because expectation M of 0, M of 0 is V of x of 0, and we're given that x of 0 equals x. When I write down an e sub x, I'm just saying x of 0 is one state. Okay? So, the expectation of M is this guy here. And I almost have that, but it's still tricky, right? Because this could be, these guys could be the same. And I'd have infinity minus infinity, I get into trouble. No, I'm still not there. This may be true. So this is true, but trying to decompose this as to having the sum of the g on the right-hand side is still dangerous. Right? If I have the expectation of this is less than or equal to something, I still could have infinity minus infinity. Do we dare? So the only thing that's giving us trouble is this damn G term. And so what we do is we just get rid of tau and replace it by something nicer. And it's all in the notes, but let's come up with something that'll bound this guy. Let's define, this is another stopping time. So sigma n is the first time that g, and I'm throwing in a safety factor as well, g of xt plus 1 is greater than or equal to n. Okay? And what happens if I plug in capital N here? G is greater than or equal to 0. I'm summing n plus 1 terms. I'm already out of it's already violated, right? So it turns out that sigma n is less than or equal to n, or less than n actually. If I let little n get as big as capital N, this is already violated. I mean, oh no, less than or equal to. It's violated, which means it could be, excuse me, it could be the first time. Yeah. Less than or equal to, no, actually, yeah, greater than or equal to. No, I was right the first time, it's true. It's a bit subtle. If g was 0, then sigma would be n plus 1, would be n plus 1. It'd be n. No, wait, I'm getting myself confused.
Yeah, it's strict.
Yeah. And, okay. Yeah. Cool. Okay, and then you know what I'm going to do. I'm just going to use this to bound this. Okay. So that's something you'd have to check, that if I take 2 stopping times, I take the minimum, it's also a stopping time. The maximum, no. The minimum, yes. You know, and you just have to think about it well. My death example is a really good one. The maximum time, the last one of us to die is not a stopping time, because I won't observe it, most likely. Anyway, forget that. So anyway, so we get, so for that example, we get this. And I'll put in the sub x if you like. I mean, we're starting this Markov chain at x. All right. Now I can unravel. I can go through this and take the definition and just plug it in. And I get this almost. I'll have to write it down. So almost there. Now, why did I make it so complicated? It's because now I know that the sum from 0 to tau n of this, of tau n minus 1, I've got a bound, I've got a bound on this negative term. So this sum of the f part could be positive infinity, but take a look. The sum of this part is bounded. It's bounded by n, or n plus 1. I don't know. I think n. Oh. So the fact that I have this thing is finite means I can take the g part and put it on the right-hand side, and I get this. So it looks like I cheated. Well, first of all, this is non-negative, so I throw it away. I make this thing smaller. By the way, you can keep it in if you want. It's sometimes useful. So you can keep this in and actually let n go to infinity and keep the bound. That's why I was wondering if I should keep it there. I threw it away just to make things simpler. All right, so you all see that from that to that, algebra. We haven't done anything yet. What do I do now? Stochastic methods, something? What happens when I make capital N get larger and larger and larger? And what happens to sigma n? You know, it takes more and more time. There's a monotonicity here. So as I let n get bigger and bigger and bigger, this random variable gets bigger and bigger and bigger. And so does this one. And so what do I... What theorem do I use from the course you took, hopefully? No. Okay, the monotone convergence theorem.
Okay.
So I've got a sequence of random variables that are non-decreasing in n, and the limit is n goes to infinity. I can take the limit inside. So I can take the limit as n goes to infinity on both sides. So the Okay, so the monotone convergence theorem says I can take the limit on both sides, I can take the limit inside, and the limit as n goes to infinity, I get rid of the n. It becomes tau. You know, because this constraint becomes vacuous. But you see the delicateness of this. You know, I mean, I almost blew it myself. I almost tried to bring the g to the right-hand side before I had carefully bounded it. You know, it's so easy to make mistakes with infinity minus infinity. You know, and people make mistakes all the time. Okay, so, but you don't have to be afraid anymore. You can now go and erase that. You know, and tonight I'm going to go on Wikipedia and erase Cécile Jourdain from Wikipedia, and you'll be able to diagonalize any matrix you want. Okay, I promise. Tomorrow you'll be able to diagonalize any matrix. But okay, but I mean, you know, it was worth, I'm not going to go through every proof, but it's worth going through this because it really is delicate. But now we can just trust it, get rid of the capital N's. The dominated convergence theorem gives you the result. All right, and obviously one main application will be to take tau to be a stopping time like we had before, because we suggested last time that this would look like a value function, you know, in a control problem. And when we take tau to be a first hitting time, and f is a cost function, so we get a bound on a value function in terms of some things we understand. G will be something trivial, like a constant or better, and v is a Lyapunov function we constructed. And this is the thing we want to understand. So that's how we use it. Okay, cool. Yeah, action-packed. Okay. So, what the hell? Let's just say it. I'll finish the day with the simplest possible Lyapunov criterion, which is Foss's criterion. Okay, so the most basic stability criterion for Markov chains, the most boring is Foss's criterion, which says that you have a Lyapunov function that has drift of rate 1. You know, so v of x of t is crawling towards the origin at speed 1, you know, and then until the origin is here. And when it hits the origin, it could bounce up. Okay. Now, it's really annoying to have a point there. We really don't need a point. This is Foster's original formulation, and then it was extended. But you can see here we've got f of x equals 1, and g of x equals b indicator function of x dot. Okay, again, I'm using that to denote a function which is 0 everywhere except for x dot. All right. So the only thing interesting here is the fact that I can take any tau, and which tau will I take? Yeah, I'll take the one that's sitting right there in front of us. So if you take tau to be then what happens? You all tell me. We saw this last lecture, but now it's precise. You know, now it's just not genius Professor Mine making claims, but we proved this. With, you know, assuming that Martingale thing, which is not a big deal to prove. You know, the Martingale inequality that I showed you is not a hard thing to show. So what happens here? You told me last time. So we're looking at the sum up to, but not including the first return time to that state. So this whole thing is just g of 0, g of x 0, which is g of x. And f is just 1, and summing from 0 to tau minus 1, 1 is just tau. So there you go. Okay, and so there it is. And so that implies that pi exists. For, you know, this is for a countable state space chain. For finite state space chain, come on, we all know. You know, this was all motivation from queuing theory, where it was very artificial to put bounds. If you say the queues are bounded, oh great, it's always stable. Well, what if the queues are all hitting the boundaries? It's much more elegant to ignore boundaries. Take infinite queues and then prove stability. And that was the motivation there. So pi exists, that's all you get. No bounds on queue size, no bounds on anything else. But there it is. But you see, given the comparison theorem, it's a one-liner. All right? Now what if you replace So this is a version of Foss's criterion you're more likely to see, that you've got a drift condition just like this, but it's not a point, but it's a set A, and it'll be a finite set if you have a countable state space, or a compact set if you're an Rn, something like that. And it turns out just a little more machinery, and you're done. I won't cover it in this course. I'm going to give you the theorem without proof, because we'd spend too much time on the math. But under the unit chain assumption, you get essentially the same thing. You know, and you'll get a different B, and you'll get something else. You know, you'll get yeah, but I won't cover that. Cool. So I think we did it in terms of mathematical techniques. We did it all in 2 hours. Stopping times and the strong Markov property and this fundamental, one of the many ways you apply these Lyapunov conditions, and even the first, thing like that, to get positive recurrence. Remember, positive recurrence was that this was finite. there was some. You brought it up last time. I'm struggling with how to get to you all to where you want to go fast. It's really tough. I mean, we're going through like, you wouldn't a nonlinear control course. You would start off with developing nonlinear systems and stability theory and Lyapunov functions, and about a third of the way to the course, you'd start to put in control. That's too long. It's it's frustrating. So I'm going to spend the weekend thinking about maybe diverting us back to control and coming back. I don't know. Because it's just, I always feel like people get impatient spending so much time on the foundations. I'll wait for feedback from you. Send me anonymous tips. Shall we go on to the natural next step, which is to, obviously say a bit more about value functions and ergodic cost. The law of large numbers, but ergodic cost. Which we'll need, because I want you to understand why stochastic approximation and learning algorithms don't work unless you know how to use them. So we need the central limit theorem and the law of large numbers. But shall we come back to it later, just when we need it? I don't know. No? Well, I'll wait for anonymous tips. Because it's too much crowd dynamics. That's how I've always done it. And yeah. But I'll wait for you to, So, there's basically, I can develop value iteration without control. That's motivated. We need that. But a lot of the math about central limit theorem and law of large numbers and all that feels like we're going off in outer space. And so, but we could bring it back when we need it. I don't know. All right, think about it and let me know.